All right, folks, bear witness. This is April 7th, 2026, according to my calendar here. It is, roughly speaking, about 9:30 p.m., according to the wall clock over here. All right. It's a Tuesday night. Labs are all done for this evening, but I wanted to share this with you. This is an analogy to the transit method that's used in the Kepler telescopes and the James Webb telescope. What I have here suspended from the ceiling by a thread is a little Nerf ball. All right, this little spongy Nerf ball right here is in front of a light bulb. This is a 40-watt light bulb, incandescent, and I've measured the diameter of the light bulb and the diameter of the Nerf ball. And what I do with this is basically have this go around in orbit like so, right? So I can cause this to make it go into a fairly circular orbit here, all right, in doing so. Now, this is half the issue here. As this is orbiting around like this, it's going to block the light temporarily. As you can see there, it tends to blip down a little bit. And this is measured over here using this setup where we have the photometer, which is this photosensitive semiconductor device provided by Vernier on this clip here, and a 10 centimeter convex lens over here to focus the light from the distant light source over there. And so as the light bulb is imaged at this distance, we can use a screen to basically bring it to focus. And then at that point here, we mark the point and place the photometer there at that location to get a pinpoint showing up on the semiconducting piece at the front over here. That dot that you see there, the bright dot, is the image of the light bulb there. And when you do this and you collect data as the ball is orbiting around, it will provide data that looks something like this, as you can see here. Every time the ball goes in front, it dips. All right, so this is kind of like the transit method that is spoken of in the astronomy textbooks. But what I also want to point out here is that these things have a width associated with them. Let me go ahead and shrink this down a little bit this way and stretch it out this way, right? And so there is a width associated with this where there's a little bit of span down here at the bottom. And this needs some refinement. If we can get the ball to actually orbit around at a much slower pace, this will be better to be able to provide this with a nice thing that flattens out and then goes back up again. So I drummed this up here. I put this together. Bear witness. All right. Transit experiment using the incandescent light bulb and the foam ball and a pendulum, like you see here, swinging around the light bulb that's lit. And then here we have the optical bench. We have a photometer and a lens. 10 centimeter is ideal to make the image small as possible. And we have this connected to the LabQuest 3 box, which is this thing here. And this is able to collect the data. And once the data is collected, and again, this is pointed towards the light bulb or our star, right? Our light bulb in the room. I'm using a 40-watt incandescent light bulb. The LabQuest 3 data is going to look like this, where you have intensity and time mapped out like this. And from this information here, we can get orbital period of the planet. From one dip to the next, we can measure that using the little things here. So we just basically have to spread this out a little bit and basically go like that and measure the time associated with this one, and then move it to the next one over here. There we go. Measure these 2 times, subtract one from the other, and you get your period, right? You can do this for a number of the sequences there, and you'll see that it is pretty much similar because it's a pendulum, right? Conical pendulum is going to have a pretty stable period there. But what ends up happening is you get your orbital period, our simulation of the orbital period from that. But if you take a closer look at this region here, we note that it dips down like this and goes back up again. So there's actually a duration here. Depending on how slow the pendulum is moving around, you can get a fairly long dip here. Ours is moving pretty quickly. But just want to note that at this point 1 here, this is just when the ball, the Nerf ball, is entering into the front of the light bulb here, starting to dim the system. And as it dims down like that and goes to point 2 here, point 2 is when it's now starting to leave and we get proper illumination again when the ball is not in the way. And so here's 1 and here's 2 over here of the positions of the ball. So going from 1 to 2 basically gives a time t, that I labeled in blue here, to travel across the disk of the star, which is the light bulb. Now, if the size of the star is known, in this case here, we measured it with a micrometer, so I have that number, then you take the value of 2 times r, which is the diameter of this thing, divided by t, which is the time it takes to go from here to here. You get the orbital speed of the planet, roughly speaking. All right, and we'll call that v orbit. Okay, now there's also some other calculations or measurements you can do. Here's this other one here. Going from 1 to 2, that basically means it's just starting to cover the disk of the bulb here, the bright part. And then when it gets to 2 here, it is now going to be constant, right, as it goes across the front of the bulb there. So you end up getting a lower point here, right? But going from 1 to 2, this has this little slopey part here. 1 to 2 I labeled as the pink T here. So if the orbital speed v orbit, which we calculated up here, is known, then if we take v orbit multiplied by t, which is the time it takes to go from here to here, we can actually calculate the diameter of the orbiting planet. In other words, that little Nerf ball that I've been using, right? So let's carry on here. Using the orbital period t and the orbital speed v orbit. Okay, so given the information that we've gotten so far, this is from the graph between the 2 dips, right? We can get the orbital period, capital T. The orbital speed we just calculated up here using this, right? So knowing those 2 things, we can use this now, where the circumference of the orbit divided by the period of the orbit should equal the speed of the orbit, right? That makes perfect sense there. And circumference is 2 pi r, right? You divide that by t, and then you multiply both sides by t to end up with this. 2 pi r is equal to v orbit times t. So capital R is going to equal v orbit times t divided by 2 pi. Capital R is the orbital radius. All right, and I put a little note here, habitable zone, right? So this would be the analogy of the, let's say, Kepler telescope or the James Webb telescope, looking for planets that are away from the star, just far enough away so that the temperature zone associated with it orbiting around that star is within the range of water forming, liquid water forming. And that would be considered to be the Goldilocks zone or the habitable zone here, right? So this works out to be pretty cool. This sort of ties in with the stuff that is actually researched, right, by the Kepler and by the James Webb. We can't do this obviously here because we don't really have a habitable zone for a Nerf ball, right? But it gives you sort of a sense of what is needed to calculate that. Now, from the graph that I have, the data that I collected over here, looking at the various things that we have here to calculate the period of orbit, I used the first dip in the graph to measure from the lowest, the low dip to the next low dip, right? The time intervals. So in other words, from the lowest point here to the lowest point here, right? And I did it for 2 different intervals. I ended up getting 2.0 seconds, 60 seconds for each one. So I presume that's the standard, orbital period for this thing. Now, I also calculated the blue T, which was this thing right here. The time it goes from this point here to this point over here. It wasn't as easy, but I was able to try to do it. If we have a slower orbiting planet, it'll come out to be much, much easier. But I did it by taking a look at these things here, spreading it out, and shrinking it down this way. This is not very manageable here, but you get the idea, starting from this point here down to the point, let me go back over here. Yeah, from here to here, right? And so in this example here, we start at the top of this thing, so somewhere right around here at the top, and we get to the lowest it goes down to the lowest point and it starts to climb. Not there, but we assume that this is a point here. Let's move this over just a little bit more, right around there. Okay, so I took that interval there, going from the top to the part where it just starts to climb. I just used that number just for the sake of it, right? And so I used that and figured out the number for that to be 0.1 seconds. Okay, and so using that now, wait a minute, 0.1 seconds? Yeah, okay. So I did that. The size of the star, I measured using a caliper, which is the diameter of the light bulb, to be 6.052 centimeters for the incandescent light bulb that I have out there in the distance. And then, so from that, I was able to calculate out the orbit of this thing, the speed of the orbit to be 60.52 centimeters per second, and then doing a calculation with the orbital speed and the period, which I found to be 2.0 seconds divided by 2 pi, I got a radius of 25.04 centimeters. All right, now again, this is my first attempt at doing this. The second attempt was a little bit better because I was using a different interval there, and this one turned out to be a little bit closer to home, I think. T is 3.80 seconds minus 3.65 seconds for the interval that we have here. This one, right, from here to here. It was a little bit easier to read on the next interval. So I did that and did the same calculation. So I got 0.15 seconds for that. And then the diameter of the bulb there divided by 0.15 seconds. This gives me the orbital speed being 40.35 centimeters per second. Sorry, my bad. This should be centimeters per second here. Okay, centimeters per second. And then the radius here, r is equal to v orbit times t. So 40.35 centimeters per second multiplied by 2.0 seconds for the orbital period divided by 2 pi. We end up with 16.69 centimeters. So this radius here is the radius of the orbit of the Nerf ball going around the light bulb. And that sounds reasonable. I mean, the other number was reasonable too, but this one is a little bit closer to the value that I was using in terms of that. It's roughly speaking about 15 centimeters away from the bulb where the Nerf ball was sort of like going around and around. So that is within ballpark. Okay, so that's reasonable. And so this can lead into discussions associated with habitable zones and all that other stuff, right? By looking at the characteristics of the star, the temperature of the star, how far must an object be away from that star in order to have liquid water form, right? And so that's more of a complicated issue there, right? But you know, the astronomers tend to work with that stuff that are more knowledgeable in that stuff. But for this is adequate to at least bridge the gap of knowledge of how to be able to do that. Now, T1 here, this is the time it takes to go from, let me go back up here to here. So it's a very, very short jump here, going from maximum to minimum here. And we're basically taking a look at when the ball goes from this point here to this point over here and continues on this way. So before it starts to move on this way, we're trying to capture the interval of time between 1 and 2. All right, and this will give us information about the diameter. So here we go. 1.15 seconds minus 1.10 seconds between those 2 points gives us 0.05 seconds for that time interval there. And so I take the diameter of the planet here to be 40.35 centimeters per second, which is the speed that I calculated up here, right, with the measurement of that interval earlier. And multiply that by 0.05 seconds, okay, this time here. And I end up with 2.0175 centimeters. So this should be the diameter of the ball, the Nerf ball. The actual diameter as measured by the calipers is 2.180 centimeters. So the percent error between these two here, if we count this as the reference number, is 7.5%. Well, that's good enough for science, right? So this is doable. In terms of the context of a lab, right, for Astronomy 10L, beginning astronomy. They get their measurements of the orbit there, and they do some simple calculations and analysis of the data here. One thing we have to focus in on is getting that ball to move slowly across the disk of the light bulb, right, in front of the light bulb there. Right now, it's just swinging from a thread from the ceiling there, as you can see. And so it's slow, but it's not slow enough, all right, to produce that nice plateau at the bottom, or the valley at the bottom of each of these things here. It's a little too quick, as you can see here. It's a little too quick in terms of what is going on. But even with these preliminary calculations, it seems to give us some reasonable numbers. All right, so I think this is a doable lab. My apologies for so many calculations and such, but this is meant for a college course, right? And using simple equipment here of what we got in terms of Vernier equipment, we're able to, mimic the technique that's used in terms of the transit method, right, for distant stars, looking for exoplanets. So I hope this has been helpful. I hope that, my name is Mike Masuda. So if you happen to use this in your lab, wherever you see this, that you mention my name. Okay, I'm hoping to be able to at least get remembered for something here for this, right? And hope that this has been helpful, and hope that people are able to use this in a resourceful manner, a useful manner in the future. All right, thanks everyone. Bye.